Okay, we've talked for a while now about how if a function is increasing, its tangent slopes at given points on that interval are positive, and how if it's decreasing, tangent slopes on that interval would be negative. So let's just formalize this idea. If the derivative on an open interval is positive, then the function is said to be increasing on the closed interval. You might wonder about this difference between open and closed. Remember that we can't do the derivative at the endpoints of a closed interval, but we will still consider those points to be on the interval where the function is increasing. So if the derivative is positive, the function is increasing. If the slope of tangent lines is negative, then the function is decreasing on the open interval. So we know when a function is increasing and decreasing. So when can it change between increasing and decreasing? Well, obviously if it's increasing when the derivative is positive and decreasing when it's negative, one place where it could change would be when the derivative is zero. Okay? And the derivative is zero at horizontal tangent lines. But I do have a couple of horizontal tangent lines here, for example right here, where the derivative or where the graph does not change between increasing and decreasing. So a function may change between increasing and decreasing when the derivative is zero, or when the derivative is undefined. I've got a point here where there's no derivative, we've got a cusp, as well as when the function has a point of discontinuity. So I have an asymptote here, but the function did change between increasing and decreasing there. It was decreasing, then it was increasing, and another point of discontinuity, it was increasing, and then it was decreasing. So a function could change between increasing and decreasing when it's discontinuous or when the derivative is zero or undefined. But that's not for sure. We'll have to check that out whether that happens or not. Finally, just in terms of one term we're going to use quite often, the point or the term critical point means the derivative is zero or undefined. Okay, our next concept is concavity, and concavity has to do whether the graph sort of bends in or bends out. So this would be considered concave up right here. This would be considered concave down. Some people like to think of concave up means that the graph would hold water. Concave down, the graph would not hold water. All right, in terms of calculus, how is this term defined? So if I go from left to right on this function, I have a negative slope, and as I move from left to right, you'll notice that my slopes are increasing. They were negative slopes, they've come down to zero, and now they're getting bigger and bigger, until I get to a point right about here. And then the slopes they're positive, they start to decrease to zero. Okay? Now this is the key distinction about what we mean by concave up and concave down. So just to go back, if the slopes are increasing, if the derivatives are increasing, it's concave up. If the derivatives, the slopes, are decreasing, it's concave down. That is the essential determiner. All right, so let's just put this together. If the first derivative is increasing, now, we just finished talking about what it means when something's increasing and decreasing. And when something's increasing, its derivative is positive. So when I say that the first derivative is increasing, that's equivalent to saying that the second derivative is positive. So when these things happen, the graph is concave up on the interval. Okay, now let's look at it in terms of concave down. So just to run through it again, if my slopes are decreasing, if my derivatives are decreasing, when something's decreasing, its derivative, in this case the second derivative is negative, we will be on a concave down part of the graph. When may concavity change? It may change, obviously, when the second derivative is zero, because that would be a transition point between a positive or negative second derivative. It might occur when you've got a second derivative which was undefined. Right here, this point right here has a first derivative that's undefined because we have a cusp. So obviously the second derivative would be undefined, and you can see we have a concave up part of the graph and we have a concave down part of the graph. So concavity could change, doesn't always, but it could, as well as points where the function is discontinuous. So for example, the asymptote, we're going from a concave down part to a concave up part. And final term or vocabulary term to know for this section is an inflection point is a point on a function where concavity actually does change. Alright, so in this case right here, that's an inflection point because concavity changed. Okay, let's use what we've just talked about to analyze this function. This is a function we know the shape of from previous years. It's a cubic. You can see the function, you can see where it's decreasing, then increasing, then decreasing. So we're going to come up with that analytically using our calculus knowledge. And there also seems to be an inflection point around here somewhere. So keep that in mind. We'll maybe be getting x equals 0 perhaps as an inflection point when we do the analysis. So we're going to begin with increasing and decreasing because that relates to the first derivative. The first derivative would be 12 minus 3x squared. And when the derivative is positive or negative, it's decreasing or increasing. So if I were to find out when it's 0, that would be a possible transition point between increasing and decreasing. So the derivative is 0. When x is plus or minus 2. These are called our critical points. Remember, our critical points are points where the derivative is 0. These are points where the function may change between increasing and decreasing. Now to figure out whether the function actually does, I'm going to analyze this through a number line. And we're going to use this format quite often. And what we're looking at are comparing the sign of the first derivative to the effect on the original function. Okay, we need to know where the first derivative is positive or negative. I know where the first derivative is 0. It's at these points. So where it's positive or negative would have to happen somewhere in between. So I could simply plug in a value in between these two x values. So for example, at x equals 0, if I plug 0 into my derivative, I would get f prime of 0 to be 12, which is a positive derivative in this section. And a positive first derivative tells me that the original function is increasing. And then I could test intervals in the other two sections. Instead of testing intervals, what I could do is, if I actually know the shape of the first derivative graph, which in this case is a parabola opening down, and these 2 and negative 2 would be the zeros of that derivative, I could just look at where the derivative is above the axis, the derivative is positive, and where the derivative is below the axis, the derivative is negative. So the derivative is negative here because the derivative graph is below the axis, and it's negative here. A negative derivative means my original function is decreasing. So to summarize, f is decreasing when f prime is negative, and this occurs between negative infinity and negative 2. Remember, we include negative 2 in our increasing and decreasing interval, union 2 to infinity. There's no endpoint to infinity, so those are open brackets. And we are increasing when the first derivative is positive, which is everywhere else, between negative 2 and 2. Okay, let's look at concavity next. Concavity could change, might change, when the second derivative is 0. So we need to look at the second derivative of the function, which, if I look back to the top, the second derivative would be negative 6x, and the second derivative would be 0 when x is equal to 0. So this is a possible change in concavity. If it is a point where concavity changes, we'll be calling it an inflection point. So, does the second derivative change at x equals 0? So now we're going to look at the sign of the second derivative compared with the effect on the original function. Alright, so I've got two intervals to test. Let's test x equals -1 into my first derivative. F double prime of -1 would be 6, which means we get a positive second derivative. And if I look back at what I talked about earlier, that means that the original graph in this section is concave up. And here at x equals 1, the second derivative would be -6. A negative second derivative means I'm concave down. Okay, so therefore we're concave up if the second derivative is positive, and that occurred when x was less than 0. Concavity intervals are always open, and it's concave down. The second derivative is negative when x is greater than 0.